Okay, here we are. I just want to go over some notes with you while I'm away. I'm a little bit unsure of right now whether the amount of importance of these topics, they seem to have taken a bit of a backslide in the new curriculum, but you're still going to need to know these for applications, and especially when we get to titration curves and stuff like that. So topic number one, we're starting on page 223. Is the hydrolysis. So hydrolysis is a reaction with water, and you might wonder what happens when a salt dissolves in water. Does it change the pH of the water, or does the solution got a pH other than pH 7? And the answer is simple. It depends. It depends on what ions are found in the salt that you're talking about. So I've started here with a little bit of a preamble. The key here, though, is that anions in this box here, anions derive from weak acids, such as acetate. By the way, we're going to eventually change this over to calling it ethanoate when we do our organic chemistry, so I might flip-flop back and forth, or nitrite. When acetate or ethanoate dissolves in water, it forms a basic solution. I'll show you why in a few minutes. Cations derived from weak bases will form acidic solutions. Okay, so we're really just concerned with ions that come from weak acids or weak bases. So here's acetate here, CH3CO, Chiku, as you guys like to often call it. And we know that it's a weak acid. Acetic acid is a weak acid, likes to hang on to its proton. So when you take acetate and combine it with water, it's going to grab off a proton from water and leave behind an OH minus. So we'll get this, CH3COOH, there's your acetic acid or ethanoic acid, plus OH minus. And you can see, because there's OH minus, our solution is going to be basic. It's just like dissolving a base in a way. Okay, and so that links up to this first statement here. So this would have a Kb associated with it, and that's its conjugate acid, as you're well aware, and that's got a Ka. This you might be interested in. I know with one of the classes, I think I developed this earlier. I can't remember which one. I think it was the A group. If we take acetic acid with water, of course it dissociates into H3O plus acetate. There's the conjugate base. The Ka here would be the concentration of H3O plus times the concentration of CH3COO minus over the overall concentration of CH3COOH. Here's what we've just done. Here's the reaction that we've just talked about. If we talk about the Kb of that, we are going to have the concentration of COOH times the concentration of OH minus over the concentration of CH3COO minus. And remember that the concentration of water in both cases is constant, so it's left out of the expression. Well, what I've done down here is I've just multiplied Ka by Kb. I've brought these down for you, and if you look very closely, we get a really cool relationship that will cancel with that. The acetate will cancel with the acetate, and if we look at it, if we take Ka times Kb, we get the concentration of hydronium ion times the concentration of hydroxide ion. And that, you might recall from an earlier lesson, is Kw. Okay, so there's a pretty useful relationship for you to use if you want to use it. If we turn to the next page, page 224. Okay, so you can find the Kb of any weak acid using that relationship. Ka times Kb is equal to Kw. For instance, if you had to do this, I don't think you'll have to, but if the Ka for acetic acid is 1 times 8 times 10 to the minus 5, what's the Kb? Well, simply the Kb would be the Kw, 1 times 10 to the minus 14, all over 1.8 times 10 to the minus 5. And if we work that out, it becomes 5.56 times 10 to the minus 10. I'm going to use this number a little bit later, although you probably will never have to. So anions derived from strong acids. Now this is the hard part that some people get a little bit confused with. Anions derived from strong acids, such as the chloride in HCl, and cations derived from strong bases, such as sodium from NaOH, do not hydrolyze. They don't react with water. Okay, so the chloride, there's no way, I'll just write up here, but no way chloride plus water is going to go back to hydrochloric acid and OH minus. It's just not strong enough. Will not work. Now, the biggest problem students have is, how do I know? Well, I'm just going to say, know your strong acids and your strong bases. Okay, you got to know those things, and there'll be a list a little bit later in the note. I threw in an example here. I don't think you'll ever have to do this calculation. If you're interested, we'll just do it. What's the pH of a 0.1 molar sodium acetate solution? So you dump this in. This is how I tend to do it. I take sodium acetate. You dissolve it in water. So what are you going to get? You're going to get sodium ion, and you're going to get acetate ion. And then you look at these individually. Well, sodium, I just said, derived from strong base. Derived from strong base, therefore does not hydrolyze. Okay, so you got to know these things. So sodium, potassium hydroxide, those kinds of things, calcium hydroxide, they completely break up in water. They're not strong enough to pull the H off of water. Or the OH for that matter. This one is strong enough to hydrolyze, okay, and so this one does hydrolyze, all right, and so what we go here, we say CH3COO minus plus water, so it's going to pull a proton off the water, and we're going to get CH3COO H plus OH minus, and then we do our little table as you've been taught to do before. So we have these three constituents. Whoops. My initial change final, 0.100 minus x, x, and x. So I have 0.1 minus x, x, and x. So my Kb is going to equal concentration of these two over that. So I'll just put in the number is 5.56 times 10 to the minus 10. It's going to equal, well, here let's Kb is going to equal the concentration of acetic acid times OH minus over acetate. So it's going to equal x times x, which is x squared, over 0.1 minus x. Whoops, minus x. Sorry, I'm not writing very well. I'm kind of on an angle here. And the x is so small, if we look at x and the value of our Kb, the value is so small that it really approaches 0. So I can solve for x. 5.56 times 10 to the minus 10 equals x squared over 0.1. X turns out to be 7.45 times 10 to the minus 6. The POH is 5.5. Is it 5.12, and so my pH is 8.88, as we expect it should be. Basic. Now, again, I don't think you're ever going to have to do that calculation. I'm not really sure, but from my reading, I think that this is really sort of taken a back seat to some of the other things that we're doing. Okay, so now, where do we go from here? Well, again, we're not going to have to do much. There's our calculation there. This is page 225. And sodium, here's something interesting. Sodium cyanide has a pH that really drives the pH. And if we look at sodium cyanide, or hydrogen cyanide, the acid, the Ka is 10 to the minus 10. You can see it's quite a bit weaker than acetic acid. So it's actually going to drive the pH up. So, you know, as weakness goes up, I guess you could say the A goes down, and the weakness goes up, and the pH then will go up. Okay, so there's something. We can do the same thing with excuse me. We can do the same thing with. Oh, I'm tired. Ions that are derived from weak bases, and they're going to do the same thing. So in this case, it's going to donate a proton to water, and so we're going to get NH3 plus H3O plus, and you can see now we're going to be acidic. I'm not going to do the calculation on page 225. It's no longer necessary. I'll take that out of next year's notes. Okay, and so as a now, just for your edification. If we look at page 226, there's some information there. So cations of group 1A metals, as well as calcium, strontium, barium, do not react with water. They're from strong electrolytes, strong bases, and they will not hydrolyze. Hydrolysis of other metal ions, like some of the transition metals, if we look at this iron, the hexaquo iron 3+ ion, it will hydrolyze with water, and it will pry or add a proton to water, and we'll get an acidic solution. So there is something to look out for. Your 4 cases are this: the salt of a strong acid and strong base will not hydrolyze. Like, neither ion will hydrolyze. Okay, so if you dissolve sodium chloride in water, you don't get any change in the pH. The salt of a strong base with a weak acid, okay, the strong base, the potassium will not hydrolyze, okay, but the acetate will, or the nitrite will, or the cyanide will, and so you will get OH ion, and your pH will be greater than 7. The salt of a weak base and a strong acid, well, the ions from the strong acid will not hydrolyze, but the cations will, and they'll produce H3O+, and so you get a pH less than 7. And then the hardest condition to figure out is if you have the salt of a weak base and a weak acid. And if you have one of those, then it's a bit of a dog's breakfast. Whichever one is weaker is going to drive the pH in the direction that it normally would. Kind of a funny thing. Ammonium acetate has a Ka of 1.8 times 10 to the minus 5, so acetate is weak and ammonia is weak, but they have the same value, so they actually don't affect the pH at all. But if you had ammonium cyanide, the Ka of hydrogen cyanide is 4 times 10 to the minus 10. It's quite a bit weaker than the Kb, and so you're going to find that it will dominate in the when you dissolve cyanide in water. It's going to dominate, and it's going to drive the pH up, because you'll get hydrogen cyanide plus OH minus. There's a few questions there on page 410, numbers 3s and 4. You can just give that a try, and just try and keep these rules, or the rules that were on the first page. Let's keep those in mind when you're trying to decide what happens with a salt in water. Thanks a lot.